I love this lesson. It's so practical. It's great. Okay, let's start with a fairly basic problem, and it is going to involve a camper that drops a cigarette in the forest fire. There's a couple little public service announcements here, and the fire spreads in the shape of a circle. A lot of times, if it's geometric, you're going to have a shape that's listed or mentioned, and the radius is increasing at a rate of 2 feet per minute. Let's just stop right there and start writing down what I know. We know a number, and it is 2, and it is 2 feet per minute. Now, on a related rates problem, I generally like to list everything I know over on the side and then just start working things out over here. That's just my strategy. You do yours. This represents the rate of change of the radius, and it is feet per minute. So it is the rate of the radius with respect to time. We call that dr dt. At what rate is the area of the fire growing? Okay, so they are asking for the rate of change of the area with respect to time at 10 minutes. Okay, so we know that we're dealing with 10 minutes. We have just listed everything that we know with one exception, and the exception is the fact that we know that this is a circle. So we're dealing with a circle. So camper drops a cigarette and it starts a fire and it spreads in the shape of a circle and it goes and it goes and it goes. Well, the radius is increasing at a constant rate of 2 feet per minute, but as this increases, the area is not constant. So here we go. Let's switch colors. Let's do this. The area of a circle is pi r squared, and nobody is surprised at that. So here's what I'm going to do. I'm going to take the derivative of this. Why? Because they gave me some rates, and so I know I'm going to need to. We're going to take the derivative of A with respect to time, and we're going to take the derivative of pi r squared with respect to time. Getting a little sloppy. I'm squeezing it in there. I'm going to d dt this side and d dt this side. The derivative of A is d a dt. The derivative of pi r squared is 2 pi r, and because this is a t and this is an r, this is some implicit differentiation without x's. This is with respect to time. Because we're taking the derivative with respect to time of r, we need dr dt, for the same reason we needed dA dt here. So what I want to do is figure out the rate of change of the area, which is what they asked. So dA dt equals 2 times pi times the radius, and the radius is, I don't know the radius. That's okay. Come back to it. This is my strategy. I like to jump straight into the calculus and then just start working through it and realize, oh, there's stuff I don't know. And then you can back up and find that stuff later if you need to. So I don't know the radius. I do know the rate of change of the radius, which is 2 feet per minute. And I'm not going to put the units in there right now. I probably could, and I might in a second, just to demonstrate why the units work out the way they do. But let's back up for a second and find the radius. I don't know the radius. But that's okay. We can do this pretty easily. So I'm going to come over here and I'm going to find the radius. I have to back up and do a little algebra before I finish what looked like calculus. The calculus part is over at this point. We just took the derivative. So the radius is increasing at a rate of 2 feet per minute. At what rate is the area of that fire growing at 10 minutes? Well, the radius is, let's see, we've had 10 minutes at 2 feet per minute, and this can happen in your head. I just want to write down what it is because I didn't want to just say, oh, it's 20, and people wonder where the 20 comes from. The minutes would cancel, and the radius would be 20 feet. Okay? So we have 20. Well, let's multiply this whole thing together because we're looking for the rate of change of the area, and that gives me 40/80 pi. And let's put units on this. I'm going to put units on pretty much all of these that are some practical geometric thing or something where, there is a clear defined unit. And in this case, we're dealing with the rate of change of the area. Area, in this case, is measured in square feet. And it is a rate, so it's square feet per minute. Okay, just to clarify a little bit here. And well, also, by the way, we're going to multiply that out on a calculator in just a minute and get the actual decimal answer too, but let's hold that thought. This 2 is constant. Pi is a constant. This 20 was feet. So feet, you don't have to write this if you don't want to. And then this 2 was feet per minute, which is why all of this worked out to be square feet per minute. Isn't that neat? Okay, let's finish the problem. This is finished, it's fine, but let's finish, and I want to find out what 80 pi is so we can have something a little more practical. And in this class, we always round to 3 decimal places. You can go more, but you never go less. So 251.327 square feet per minute. Let's put this in context to make sure we understand it. Somebody drops a cigarette, starts a fire. At 10 minutes after the cigarette was dropped and the fire began, the area of the fire is, notice this is positive, is increasing at a rate of 251 and some change square feet per minute. And the radius is 2 feet per minute.